And now we have moved to real-like modeling and simulations. Now, real-like modeling and simulation is in practice in most part of the world right now. Many regions have adopted this real like or true modeling and simulation techniques. But some of the regions, they have mixed bag, and the others, they are still stuck uh, to empirical or semi-empirical ones. So the intent of this lecture will be a comparison between the merits of modeling and simulations with the limitations of the empirical based soil structure interaction. So in order to fulfill the intent of this lecture, this is the outline that I would be following. Uh, I will just start with just a brief conceptual discussion on what soil structure interaction is meant by me, in fact, or what will be the essence of soil structure interaction that will be followed in this lecture. Then I will just reinforce those ideas with discussions on case studies and examples from these areas of soil structure interaction, like raft foundation, piled raft foundation, excavation support systems, tunnels, earthquake loading, and there would be a few examples from ground improvement systems also. Finally, I will conclude, and I will have few recommendations how to go ahead, or what should be the roadmap that should be adopted to shift from empirical, semi-empirical to the real-like modeling. So let's uh, start with soil structure interaction. In fact, although when we speak soil structure interaction, it seems it's a one phrase or one word or a couple of words, but in fact, it has three distinct elements. One is soil, other is structure, and third, that is also very important, that it's interactions. So we call it together SSI. Now, if we look at this just a sketch that we have a soil and we have a structure. So almost all of the civil engineering structures we know, they interact with each other. And I have mentioned that we have always been practicing soil structure interaction since the advent of civil engineering itself. So this interaction, in fact, and we have learned over a period of time that these interactions are quite complex in nature. They are not simple. But unfortunately, what's happening that we, in empirical or semi-empirical concepts, we are using or we are converting the soil side, or the soil side especially, in the form of oversimplified equivalent soil elements. And this is the problem. So once we do this one, either we are over designing our system, we are uh, doing an uneconomical design, or we are moving towards unsafe side. So these are the two implication of using oversimplified equivalent soil elements. And this is what I will be, this idea I will be reinforcing through all the discussions and case studies in the following slides. So as I mentioned before, that now we have, at least during the last 2 decades, finite element method and SSI based software, they have made these real-like SSI modeling a reality. So the message is that which will be carried over throughout this lecture, that these interactions should be realistic and not the simplistic version of either of these. Now, what's happening is that in some cases, or in most of the cases, soil is being simplified while we are having a very advanced level of structural models, but soil is being simplified in the form of very simple elements. And vice versa also. Sometimes we have highly complex soil models, and we are converting the structural loading into simplified forms like UDLs, uniformly distributed loads. So this is the message With this message, again, I would like to highlight before I move into the case studies that I will be comparing the conventional methods based on empirical or semi-empirical concepts and the real-like SSI modeling. Now, these are the two ends of the spectrum. We have on one side very simple empirical methods, and on the other side we have the most advanced type of modeling and simulations. There could be many versions that exist in between that one. So, but it could be like a one step, two step, or maybe a little more further towards the SSI modeling, but still there are a lot of limitations associated with that one. So I will be comparing, I'll try to compare the wider ends of this spectrum. So let's start with the raft foundation. Our first case is raft foundation. Now, when we design a raft foundation, what's happening in many cases, we are adopting Pinker model, and most commonly known as modulus of subgrade reaction concept. Now, if we look at this model, very simple model, we can start seeing the limitations of this model, that we are representing the soil by the discrete springs. But the soil is not discrete in nature, it is a continuous medium. So, and also we are considering these discrete springs as elastic springs. And reality is that the soil is not elastic. Soil is, in most of the cases, soil is elastoplastic in behavior. So elastic behavior cannot represent the soil. And also there is no lateral connection between these springs, like each spring is acting independently. So I'll just further highlight this concept over here. Now we can see here, let me take the pointer here. Okay, we can see here there is a raft foundation placed on the soil. And if we convert this soil into springs, it will be just like that. Okay, so we have two fundamental differences which I have just mentioned in the previous slide. The first one is that soil is a continuous medium. We call it continuum. While if we use modulus of subgrade reaction concept, it's basically converting this continuous medium into springs. Okay, and like for example, once the raft moves down, that's only the bottom part I have moving, the upper part just for the sake of simulations. Okay, soil will compress like this, but it will dilate like this one, or compress like this one also. So soil does not move only in the vertical direction. There is a lateral component that is very important to be incorporated. This is basically, we say, shear transfer of the forces. Okay, so springs which we use in the modulus of subgrade reaction concept cannot represent this one. Moreover, if soil is compressed, for example, over here under this column, soil is compressed, its effect is basically goes to the other places also. But when we use discrete springs, this effect is absent. Okay, so the second difference, in addition to springs versus continuum, is the elastic behavior of the springs versus the elastoplastic, which is the real behavior of soil. I can try to represent this one through these plots, and we can see over here that we have a line which is basically an elastic model, and this is what we are assuming. But the real soil behavior is bracketed in between these two extremes. We can have a soil behavior like this, or we can have a soil behavior like this, and we can have an infinite number of behaviors incorporated in between. So whenever we are assuming soil to behave like this, so it is for the soil is not an elastic material. It can be, but like for example, for this model, a very small initial portion of the soil will be elastic. After that, it will behave like an elastoplastic material. And for this model, it's purely elastoplastic. Not it doesn't have any kind of elastic spring over here. So we can see here, if we compare these assumed versus uh, uh, assumed versus the real models, we can see what are the implications. Like, for example, if we're assuming like this and the real behavior is like this, then we are definitely over designing our system. Okay, and if we are assuming like this and the real behavior is of the soil is like this, then there is an under designed effect, or we are definitely causing some safety issues in the structure. It could not be a big safety issue, but definitely some durability issues come into picture. This is I would like to highlight like this one. We see here when the raft dishes like this, there is definitely a structural distortion. We call it structural distortion, and we have put a limit. Well, there are different versions of this limit, but there is a limit that if we have to keep our structure crack free, then we have to opt this structural distortion limit. But what happens, for instance, if we are assuming like this over here, if you follow my pointer over here, so and the real behavior of soil like this, then definitely in reality it will have distortion that it will be much higher than that, and the slope will be steeper over here, and it will result in the formation of cracks uh, along the column and foundation joints or within the foundation. So this seriously undermines the long-term durability of the structure. So we can see here that if we do not cover these two concepts in our model, either we are over designing and doing uneconomical designs, or we are under designing and we are cutting on the durability of the structure. Okay, so these concepts I can further support by a case study or a study carried out by these gentlemen, in which a raft foundation was modeled in three different softwares. One was the STAD software, STAD Pro Foundation, in which modulus of subgrade reaction concept is there. A Plexus 3D model, which is basically a 3D finite element method based software, and it can model the real column loading as well. Now, and also a 2D finite element based software, which is Sigma W. So in this study, basically, different thicknesses of raft and different strengths of the subgrade soil or the foundation soil, we can say, uh, was permeated, and different combinations of raft thicknesses and soil strengths were basically adopted in this study to understand the comparison between STAD Pro results and the finite element model based software. Although it's a big study, but I'm just highlighting or just presenting a few results out of these, just to built upon the concept that I have started talking about. We can see here, this is basically the base pressure result from the STAD foundation software. It's a 0.5 meter thick raft foundation on soft foundation, on soft soil, you can say. So you can notice here that because of the discrete spring effect, you can see we have a concentration of stresses over there. Now, if I compare the section of this one, which is this one red line, we can see here, this is the STAD foundation result versus the sigma W, which is basically 2D version of finite element. We can see sigma W has covered these localized stress concentration or column loads by spreading the load to the adjacent soil in the continuum. While STAD foundation, since it is based on the single spring action, it does not transfer forces among each other. We have this kind of behavior. Now, if we look at the other side of the spectrum, that is 2 meter thick raft foundation on hard foundation. Now we can see that STAD foundation has shown a uniformly distributed pressure. Okay, it has shown different uniformly distributed pressure or soil pressure from the beneath because of the rigidity of the foundation and rigidity of the soil. But we can see here that sigma W is coming up with lesser pressure, first of all, and it has some edge effects also incorporated because STAD, if we consider, like, for example, a spring at the edge only, it will give us a reaction like this, but we have some hogging effect uh, in which has been captured by the Sigma W software. Okay, now if we look at the settlement, we can see here these are the STAD Foundation results. It has given us a very low settlement owing to the elastic nature of the spring only. While since we have used elastoplastic models of for the soil in Sigma W and Plexus 3D, we can see it has given us a much higher settlement. So these are the real settlement. Now, if you just recall the slope which I mentioned for the maximum slope allowed for the structural distortion, we can see that in this specific example, modulus of subgrid reaction concept has failed to capture that one, while the other finite element based software, they are really capturing that concept. So we can see the steepness of the slope over here. So this is how we can compare the things uh, while using compare the things for the empirical and real modeling in the software. Okay, this effect can be further reinforced by a study by Lee and Salgado which was carried out in 2002. These gentlemen, in fact, highlighted the concept that if we go for, like for example, elastic model only, which is not the reality, while the soil behaves as elastoplastic, which is the actual behavior, we can see that how far these are from each other. For like for example, any value of the load like 0.5 MPa, we can see there is a couple of centimeters difference in between uh, these two models. Now, finally, if, like for example, if our raft foundation, which has a loading from the columns, and we have a reaction from the soil, it is presenting something real. Only then we'll be getting the right bending moments and shear forces in the slab. Otherwise, it has been seen that heavy reinforcement results if discrete springs are used, because we have very high base pressures and we may have bending moment and shear forces far from the true ones. So this is regarding the raft foundation. Now I'm moving to the second case, which is basically piled raft foundation. Now, again, just to introduce that a piled raft foundation is where we have a raft foundation and we have connected piles with it. We may have disconnected piles, but we are considering here the case where the piles are also connected with the raft. Now, again, there are two major differences. The first difference is this. Again, piles in empirical formulations, piles are being considered to act as discrete elastic springs. So this is one of the assumption in that one. And secondly, in many cases, we ignore the raft shear. So let's see what happens for these two assumptions. The first of all, as I mentioned before, that soil behavior is elastoplastic, but also for the piles we have the real behavior is elastoplastic in nature. So if we assume or we convert soil piles in the form of springs with our sophisticated structure models, basically we are not making the right assumption. We can see this is one of the load test result on the piles. And you can see that it's all elastoplastic behavior. It's not a elastic or linear behavior over here. So with this reality, again, we'll have a problem. We may have a problem, like, for example, this is the real behavior. The red line is showing the real behavior, while these two elastic lines are showing the other extremes. So if we are considering this one as compared to this one, so we are way away from the real behavior. And also, same is true for this example. Okay, so this is one difference or limitation. The second one is that Second one is that we are ignoring the raft foundation. But problem is this, or reality is this, that we have basically, when we are talking about raft foundation only, we have two different interactions, one soil and other structure, and the interfaces we can say. But in case of piled raft foundations, we have four different type of interactions. And we can see here, let me just zoom this one, maybe if it's better. We can see here four different type of interactions. One is pile and soil interaction, which is obvious. Then we have pile and pile interaction. Okay, and we have then raft and soil interaction, and then we have a pile and raft interaction. So if we have four different type of interactions, which are basically sketched in this section. And if we are assuming the what I want to say, that we are assuming that we have just discrete springs that can represent the foundation under the raft under the raft, we are ignoring three other interactions. So even if we ignore these three interactions and we are saying that we may be on conservative side, we may not be on conservative side. We may be over designing or we may be under designing, because raft is putting a pressure on the piles as well. Okay, so we can ignore raft only if raft is not placed in soil. If it is placed on soil, definitely it will have its own stress contribution to the different pile foundations. And the piles and one pile and the other pile, they are also interacting with each other unless we have a very high spacing among the piles, which is not usually the case. So these two major differences I have highlighted for the raft foundation. And once we adopt this one, only then we can see the right type of stress distribution or bending moment, shear forces, etc. In the piled raft foundation. You can see here we have a distribution of different stresses or bending moments in this case. And we have another case where we have a different pile configuration, and we can see now the bending moment distribution is different in the raft foundation. So the reinforcement type, content, and total volume, etc., everything will change. And same is the case for the shear force diagram, which is shown over here. Let me take the laser pointer. This is the shear force diagram or the shear force distribution in the raft when we are considering raft and piles together in a real-like model in three-dimensional finite element, sorry. And moreover, once we have, like for example, a real interaction model, the bending moment and other characteristics that are required for the design of pile foundation would also be real in nature. So this is a very important aspect, because otherwise, if we are considering piles alone, we may be either again over designing, or maybe in some cases it may be under designed as well. So another important consideration during the design of piled raft is the bearing capacity. And even this is also valid for the raft foundation as well. If we look at this diagram again, Mr. Wu and Tata Sonori, these two gentlemen actually did a lot of studies on the piled rafts numerically as well as experimentally on the small scale models. And they have found big discrepancies when they were studying these cases. And they found that the load settlement curves and other parameters, they are quite different when they determine these experimentally as compared to the numerical equivalents based on the usually adopted empirical concepts. So these two gentlemen have provided a lot of case studies. I'm just showing you one of these, so you can see the difference over here also. I was talking about the bearing capacity. Bearing capacity basically of piled raft foundation, especially, and raft foundation also. It's basically based on the construction sequence Okay, and the behavior of the soil during excavation and construction of pile foundations, and then putting of the raft foundation, and finally we have the building load. So if we have made like a real like model, we can simulate all these stages. Like for example, in this plot, I'm just showing that when we excavate, we have a heave, then we have pile construction, and then we have a raft construction, and finally we have raft loading. And this provides the best bearing capacity judgment for pile draft cases. Because if we involve several empirical methodologies or only elastic ones, uh, etc., then we may not end up in getting these numbers. So here we have, like for example, a compensation. We called it excavation compensation concept in its real sense. Okay, so the third case is regarding the excavation support system. Excavation support systems, we also called shoring systems. Now, again, since I'm comparing the empirical concepts with our modeling concepts, all our empirical based methods for the design of excavation support systems are based on, or most of the methods I can say are based on limit equilibrium method. So they are strength based methods. But what we are looking in our excavation support system is basically something which should be based on the stiffness, because we are not only worried about the collapse of the system or failure of the system, we are worried about its deflections and especially the displacements which will occur behind this shoring system, because we can have buildings over there, we can have sensitive structures over there, we can have infrastructures over there, or we may not have anything on behind the shoring system. Like for this example, for instance, we can see on two sides we have building structures where our requirement will be to design a system which should not move at all, okay, or it should not cause any displacement underneath the existing structures that could be detrimental for the safety and the structural integrity of these structures. But on the other two sides, we are relaxed. So we should not be worried about the total displacements, because we will have a liberty to design a light system on these two sides, and we can have heavier system on these two sides. So our systems are basically stiffness based. Requirement is stiffness based system, but empirical methods, they are based on strength. So we can do it through finite element modeling with the soil structure interaction concepts incorporated these models to get this one. If we look at the strength-based methods, we have like three pressures only. We say at rest pressure, active pressure, and passive pressure. So we have either at rest conditions, which means zero movement, or we can have an active where is the maximum movement, and we can have passive for the embedded part also. So basically, in reality, these pressures do not mobilize to its complete sense. We have not an ideal at rest conditions. We don't have ideal active or passive conditions. We have something in between. Okay, this we can further understand from these two model. On the left side, this is an idealized model in which we are using springs or converting again soil in the form of springs. We have anchors, we have active side, and we have passive side. So we are considering that either we'll have a full passive, or we have active, or we have at rest conditions. While if we look at the real model over here, where basically the relative rigidity or flexibility of our excavation support system comes into picture. So if it is very rigid, its behavior will be different. The distribution of active or passive pressures will be different. But if it is much flexible, it will be again, something different from the first case. Like for this example, this is the deflected shape of the wall after the installation of this anchor. Now we can see here in this part there is passive pressure. We have active pressure only in this one, and it's a partially mobilized. It's a partially mobilized active and passive pressures, and here the pressure distribution is different. So using the empirical systems common in the market, in practice, common in practice, I will say, we cannot capture such realities. We cannot capture such realities. These realities we can capture only in case using like model this one. We can see here this is a complete model showing model in which we have struts, we have anchors, we have shoring piles, we have railings, etc. And we have, in addition to that, we have a raft foundation, and we have the main loading piles, or the piles for the structure. Now we can see here that how the interactions are taking place. There will be interaction between shoring piles and the main piles as well. Okay, there will be a deflection on this side of the entire system, and there will be like, for example, an elongation of this tendon, elongation of this anchor, and there will be skin friction on top of this anchor. So there are so many questions that cannot be answered using empirical systems. We can answer all these questions through SSI modeling only. Or like the same model, now you can see here, it is after running this model, we have seen that there is a tendency of this settlement over here. There is a tendency of settlement over here, and lesser on this side and lesser on this side because of the struts presence. Now you can see that this building is in problem. This building will be in problem if we go like this one, and this building will have least disturbance with this system. And we do have problem over here, but if we don't have any infrastructure or structure over here, we shouldn't worry about. Okay, so everything will be under control until unless there is a collapse mechanism. But a collapse mechanism again is something which is basically subjective. And in empirical systems, we have, like, for example, we are calculating the integrity of the anchors independently and the rest of the structures independently. And in SSI modeling, we can have, like, for example, even it can highlight for you our localized problems, like this is sand, and sand is flowing out of the piles if we don't provide like the complete the closure of the gap. So this is what is also possible through SSI modeling. And through this SSI modeling, once this is done, then we can have a precise estimation of deflection, bending moment, and shear force in the shoring piles. And we can have, like, for example, deflection assessment, skin friction assessment, and axial force in the anchors as well. Even in the veiling, we can have bending moments. And this will be there after all our requirements are met. Like, for example, there could be stringent requirement on the structure side, and there could be a relaxed requirement on the other side. This is how we can economize the systems. If we, like, for example, use either, again, as I mentioned, that conservativeness, which is basically a soft word for the uneconomical, being uneconomical, we'll be using the same design, the worst design, all the four sides. But with this type of modeling, we can have, like, for example, a different model on each side, and this is how we can save money. Okay, while being within the factor of safety. Now, when I mentioned the factor of safety, it's very complex, actually, system. We have seen that there are so many elements interacting with each other. But if we do SSI modeling or close to real life modeling, we can have, like, even a factor of safety determination of the entire system. And that's what usually we are worried of, because we don't know which component of the system could fail in the first instance. So we can have, like, a factor of safety determination, for the entire system, and this can give us a peace of mind that still the entire system is away from any kind of possible unsafe scenario. Okay. Now, next case is basically tunnels. Now, in tunnels, uh, most commonly, we are designing the tunnels and their support systems using one of these methods internationally. One is the rock quality based, which is called Q system, and the other is RMR, which is rock mass rating system. In both these systems, we assess the quality of the rock, then convert these into classes. And then based on these classes, we have empirical and semi-empirical concepts which on which basis or experience-based database uh, that is usually used to come up with the design of the support system for the tunnels. But with the advent of now new system, which is called New Austrian Tunneling Method, NATM, this is basically purely analytical method. Also, although there is some component which we incorporate from the experience as well. And this component is always there. Actually, I don't want to say that experience does not have any value in the modeling. Definitely, these models will groom and grow with the input of more precise experience into these models. So basically, it's an analytical model. Now the convergence of the tunnel as we do the excavation and installation of bolts, anchors, or shotcreting. Shotcreting can be done in a very precise manner and a very economical manner. This I can show from this diagram. Although it looks a little complex, let me explain it. These two red lines we can see, these are basically the load deformation curves for the tunnel roof, and this one, the bottom one, is for the tunnel side wall. Okay, this tells us some reality about the pressures in the tunnel roof and tunnel side wall. Like for example, if we install our support uh, when the tunnel is just excavated, okay, so our support system will experience very high stresses, and it will be a very heavy system and uneconomical system. Okay, but if we install at this time, so already our tunnel roof has failed. Okay, so we don't have to do something over here and we don't have to wait till this time. So we have to do in the most economical manner and most appropriate manner, and we have to provide our support at some times in between over here. Okay, and this is how we'll have like a economical and most practical solution. And these curves, red curves, are called ground reaction curves, and the curve which is for the sport reaction, we call it sport reaction curve. So sport to come up with the ground reaction curves and sport reaction curves, we need SSI modeling. Okay, and through that one, we can come up with the most appropriate time and the most appropriate type of sport that is required to be installed for the tunnels. Okay, so this was about the tunnels. Now I'm moving towards earthquake loading. Again, if we compare the wide ends of or extreme ends of the spectrum, like for example, comparing the pure empirical versus SSI modeling, we can see that we have basically three fundamental differences, or two fundamental differences, and another one will be the subsidiary one. First of all, in empirical system, empirical designs, we are assuming or we are converting the earthquake loading into pseudostatic or equivalent shear. On this diagram, you can see that this is what we are assuming for our designs. But in reality, earthquake loading basically.
Doctor,
Yes, sir.
Doctor, I have to make a little small announcement. I have to, please, you have to pause for a second. I have to make an announcement. Uh, Ladies and gentlemen, I am looking at the chat box. We have received a lot of questions, maybe who have joined us after the initial announcement I made earlier. All the questions will be answered at the end of the lecture in the dedicated 20 minutes Q&A session. Thank you. Continue, Dr. Saab.
Okay. Okay, so but the real earthquake loading is in the form of vertical and horizontal displacements. And we can see these components over here. We call it like real earthquake seismogram. Okay, so I think the difference between two extremes is obvious that in the first one, we are just considering a static force, so static horizontal force, and in the other one, we are applying a real earthquake seismogram or basically the complete history of horizontal and vertical displacement of the soil. In addition to that, the reality is that when we load a geomaterial, its shear modulus keeps on decreasing. It keeps on decreasing with the shear strain, with the increase in shear strain. So if we apply a real seismogram, we can see that there is a continuous degradation of the shear modulus also. But if we use like pseudostatic or equivalent shear, only then we can have 1G value only in our design, which is not the reality, in fact. Okay, so when we do SSI modeling, we can have, like, for example, the incorporation of the real behavior of the geomaterials, and we can have like real earthquake over there. So again, we can have both the scenarios. I'm saying we can be over designing through the adoption of pure empirical techniques, or we can be on unsafer side as well. Okay. The other fundamental difference is that in empirical based methods, we are considering just the macro level seismic zonation. This is the Pakistan map, which is showing earthquake zoning over here. We can have different versions of these, but the concept which I want to highlight, that we have bigger zones over here, and we are assuming one acceleration for this big zone. But in reality, we can have a very weak zones within a overall stronger zones, or we can have, like, for example, or soil or rock, which will behave in a very poor manner against even a medium type of earthquake or medium intensity earthquake, and vice versa as well. So that's why IBC, International Building Code, they are asking for site-specific response. Now, site-specific response can only be done through SSI modeling, in which we load a seismogram on a soil column, and then we see how does it shake. So we shake the soil column in its natural form, and this shaking is then integrated with the shaking of the building as well. Now we have a building on top of it, and we have a soil. We are shaking the soil, and along with this shaking of soil, the building will shake in this manner. Okay, and this is the real SSIE, in fact, that we have the characteristics of this building material, or the building configuration, or all this structure is entirely different from the soil and the rock on which it is lying. So the interfaces will really define the behavior of both soil and this building as well. Now, if we look at what we are getting out of this SSI, we can have a lot of information. Like, for example, in this one, if we say input an earthquake, a real seismogram on our soil column, so we will get displacement versus time at the top of the building, even top of the building, and we will get accelerations both at top of the building and at the foundation, these two graphs, and the final requirement for the design of structure, which is response spectrum analysis at the top of the building and at the foundation level. So this is what we'll be getting for the structures, for the superstructure, and if for the foundations, we can get a picture like this one. So we'll get how much deflection or reverse in curvature of the foundation. Basically, the deep foundation will take place once this seismogram is loaded on the foundations, on the soil itself. Okay, so just to further highlight, we can see here that in dams, especially, if we apply, like, for example, a pseudo static equivalent of the earthquake, it will give you altogether different picture. But what we get from here, we can see here, we are interested in the total deformation, and not only total deformation, we are interested in the stresses, strains, pore pressure scenarios during the entire earthquake loading. So I can show you one just simulation of that, how when we load the real seismogram on this dam, how its components are moving. It's an exaggerated, little bit exaggerated form of the movement, but this is how these move. And then the real pore pressures, stresses, and strains could be envisioned in this model. And once it is done, we can have, like, for example, a, a precise evaluation of the liquefied zones, or where the liquefaction has taken place. So this model can give you all this information through one SSI modeling alone. So this is how earthquake modeling has transformed into a new era, where real earthquake can be loaded on the structures, and we can get the real response, or real like response from these structures. Now, the last topic, or the last cases, are from the ground improvement, and I have chosen two different type of ground improvements. One is stone columns, and there is the foundation placed on a swelling soil or expensive soil. So let me start with the stone columns. We can see here, and I think most of us know what stone column is. But here we can see that we have a stone column which has a different diameter in this soil and a different diameter in this soil. Okay, I'll just start with this idea, and then I'm coming back to the empirical method that is being used for the design of stone columns. Preve's empirical method is the most commonly used method. Here we have, like, for example, we have area ratio, and based on this area ratio, we get an improvement factor that is used for the design of stone columns for any ground improvement project. But the problem is this, that Preve method cannot answer many questions, or it does not answer many questions. One question, as I mentioned over here, that we can see there's a large diameter over here. So I have made a sketch to just put forward all these questions which Preve cannot answer. Like, for example, we have a soft clay layer. Now, I think it's very obvious, and all of us can well understand, that stone column strength is generated from the confinement which gets from the surrounding soil. Okay. Now, when we say soft clay, it means we have lesser confinement over there. So what we have to do over here? Okay, what changes in the design, or what changes in the construction we have to adopt to get a better stone column in soft clays? And if this soft clay layer is, like, for example, couple of meters to a very high number, then can we do stone columns in such grounds or not? Okay, if we have to do, what changes we have to make in this one? Okay. And then next question is, like, for example, for the columns present at the periphery of the foundation, or columns present in the middle of the foundation. So both of these will have a different behavior, but Preves provide us the same design for all these aspects. Now, again, for the foundation flexibility or rigidity, we can see here that if the foundation is too much flexible, then the pressure it will impose on the columns, and the columns behavior will be different. And while it will be different if it is rigid, or we can say vice versa. So what basically, again, I'm putting the same sketch over here. We can see that we have a large section, and how much enlarged it should be over there. So all these questions can be answered with SSI only. Now, these are the two examples I am just presenting for the stone columns modeling and simulations using 3D and 2D finite element based software. So we can see here that this is the soft clay layer, and we can see that behavior over here. We have a different level of bulging of stone columns over there. We can have a bulging, slight bulging over here, larger bulging over here. And it is also based on how this foundation is acting, whether it's a rigid foundation or it's a flexible foundation. So this information we can get, and in the same 3D model we can see over here as well. Then the behavior of the peripheral columns, whether we have to provide one periphery column or maybe more, it also depends on the results of the or results of the simulation. Okay, and there was one case study again, a study made by these gentlemen, where Preeb's predicted settlement was compared in the field for a tank placed on stone columns, on the stone columns at this much spacing, a 12-meter diameter tank. And we can see the results. I'm just comparing the results. This was what was predicted by the Preeb. And here, this plot is basically the settlement plot for the tank, full size tank, the prototype structure. And this square is basically representing the settlement predicted by the finite element based software. So basically, in this case, there were thick soft layers, thick soft clay layers. So only modeling could provide a number closer to the actual behavior. So this further emphasizes the importance of SSI over there. Okay, the last one is basically, I'm just presenting one slide. This is related with the ground improvement when we are dealing, or one of the technique for ground improvement when we are dealing with the expensive clays or swelling soils, that we provide or we try to anchor the raft foundation or the foundation of our structure in the soil with the help of anchor piles. These are these small diameter piles we called anchor piles because these act in tension over there. So when the soil swell, basically it supply pressure on the raft, and the raft is get anchored into the soil with the help of these piles. So there are so many questions when we design such kind of system. Like example, we want to know how much hogging that will take place over there, and how much will be on the edges, and what kind of what sort of friction that will be developed there. Will there be any movement or not? I'm just pasting this one plot over here, which is basically showing that how different components of this system works. Okay, so again, empirically, we cannot get anything out of it. So we have to do an SSI modeling over there. So that's it with me, with the case studies. And I'll just make, I have made a summary, and I will just speak the same thing which I have mentioned before. First of all, in Winkler model, there is no shear transmission between adjacent springs, and there is no stress distribution in between the springs, and the settlements usually predicted by modulus of subgrade reaction, and especially at the edges, do not seem to be realistic. And stress distribution, settlement, shear, and bending moments could be more realistically modeled using the soil structure interaction based software. So this is the conclusion. And final conclusion is that precise analysis and design should lead to the most economical and durable structures. And this is what I have logically explained for all these examples over there. Finally, recommendations how to move ahead or how to adopt this one if there is still problem. There will be I mean, there are three essential elements of a realistic soil structure interaction system. What are these? First of all, there should be like a finite element based or discrete element based software which can model both soil and structure, not only soil or not only structure. Okay. Constitutive modeling of materials or input of constitutive model of materials, both for concrete, soil, rocks, whatever materials. And the most important part is interface elements or interfacing of these two big regimes. Okay, that is very important because if the interface modeling does not provide the real sense, then the sophistication adopted in like, for example, for the soil and structure will fail. And I'm not negating, maybe you can get an impression, but I'm not negating that empirical or semi-empirical concepts should not be used. These can be well used at the early stages of the design, like, for example, pre-feasibility stages or like early assessment stages. And so these can be used at these stages, and these can also be used because these definitely have got groomed over a period of time, just to know that whether where we do we stand with respect to economy and safety. Okay, how we can adopt this system? Generally, we have seen that we have structural engineers, so they are taking the simplistic version of the soils, and geotechnical engineers, they are considering structures as very simple. So they are moving independently of each other. They are moving independently of each other. So if there is a requirement of an SSI group, and it should consist of both soil and structural engineers, only then this system will work in coherence. So that's all from my side. And if there are any questions, and I really thankful to all the participants for the patience you have shown to listen to all of this.
Thank you, Dr. Habibur Rahman. It was a very enlightening and lecture with some new dimensions and new input that I am 100% sure our audience would have learned a lot and must have enjoyed the lecture too. Now we have a number of questions, and I can very safely say maybe we have to extend the Q&A session beyond 20 minutes. But we have fairly good an amount of time available. So inshallah, I will try to manage all the questions one by one. The first question is from Rizwan Mirza. Dr. Habibur Rahman, the first question is from Rizwan Mirza. And I will read the questions as it has been put in the chat box. The speaker has shown springs under columns or load points only, but practitioners place springs at a fairly close interval in each direction. This needs clarification.
Okay, in fact, I mentioned in that slide, or while I was presenting that slide, that I'm talking about two extreme ends. One is that we have discrete springs, and on the other side, we have soil as a continuous medium. Now, there are certain improvements in different softwares. They have tried to bring the springs closer. They have tried to connect the springs. But basically, if you ask me, like, again, it's in no comparison to the real soil behavior. Soil is a continuous medium. Even if we bring soil springs closer to each other, there will be no lateral connectivity among these. And each spring, again, is acting independently for each other. If we connect these springs together, okay, we are a step towards soil continuum, but not even closer to it.
Okay, thank you. I'm just saving some questions also as I'm reading them. Just give me a second, please. I'll just read the second question. Yeah. The second question again is from Rizwan Mirza. He's asking, subgrade modulus is a very elusive number. What method of determining subgrade modulus is the speaker assuming for comparing various analysis methods?
Actually, there are many methods that are definitely circulating in the industry, or being used in the industry, or being practiced in the industry. Some are being proposed by the geotechnical engineers. Some are basically have been adopted by the structural engineers. But there are many limitations associated with it. The most common is a relationship between allowable bearing capacity and the modulus of subgrade reaction. But even this method has several limitations. But the numbers which we have used were based on the actual test carried out on the soil, so that we should at least cut down that limitation. Okay, so we call it direct method, is direct method of adopting models of subgrade reaction. Others are correlations with other parameters which you are usually determining in geotechnical engineering, but we have used a direct method to determine the moduli to be input in that study.
Okay, the third question is from Suhail Kibriya, Mr. Suhail Kibriya, and he is asking, he's saying, nice comparison of SSA models. Have you validated the results of these models with the actual performance captured with instrumentation?
Uh, of course, I have shown some cases, like for example, stone columns. We have basically measured, and we found experimental correlation. Then I have shown one slide in which load settlement curves of raft models were studied by two gentlemen. They have done a lot of study. These are, I think, Japanese, and they have done a lot of studies. Like, I think, is this slide visible
Yes,
right now?
visible.
Okay. Yeah, so this study is one of the study by these two gentlemen, and we can go through, or anyone can go through their studies, and they have done a lot of comparisons between experimental behavior of pile draft with instrumentation, but they have made smaller models in the lab, and they've compared these behaviors with the numerically determined values. So there are many which we have done ourselves, and there are a lot of studies available in the market right now. Those are those provide data of these kind of comparisons.
Thank you, Doctor. Now, next question is from Rizwan Mirza again, and he's asking, in the pile mat foundation, when the mat, pile, and soil are modeled together with their own stiffness duly reflected, how would compatibility be violated? In other words, how would the three act independent of each other?
Uh, s- uh,
Should
I don't know.
should I repeat the question? Should I repeat the question?
Can you please?
In the pile mat foundation, when the mat, pile, and soil are modeled together with their own stiffness duly reflected, how would compatibility be violated? In other words, how would the three act independent of each other?
I don't know. The last sentence is a bit confusing for me. Maybe I'm not able to understand, but I have said other way around. I'm not saying they are independently acting. They are interdependent. There are four different type of interactions. I have just sketched in that. So let me come to that slide. So those are not at all independent of each other. There are interactions. And what happens actually, okay, this one. What happens actually that we are providing not only the stiffnesses, we are providing the constitutive behavior models of all these components or those elements in the system. So there is a complete behavior model. Like for example, when each element is being stressed by a load or by the element next to it, there will be a response, a behavior response from this one. So they are interdependent, definitely, and we are providing constitutive modeling, and we are providing interface elements or interface behavior models, and all this basically provides a conjugate behavior type of system.
Thank you, Doctor. Next question is from Mr. Asim Akram. And he has said, sir, as you have shown in the raft stress diagram in STAD Pro and compared it with sigma, the stresses distribution in sigma were more like uniform than in STAD Pro. But isn't it like under the columns, there will be higher stresses and diagram will be like wavy one as shown in STAD Pro results?
Yeah, actually, this is basically the difference. This is basically the difference. Like for example, this Tide Pro, since we have springs, so we have a localized effect. But when we consider soil, soil is not a spring, and I have shown over here that we have a continuous medium. We have a when we compress the soil vertically, it basically distributes the load in lateral direction also. So there is a lateral movement also. So that's why we can never have, like, for example, a wavy type of action for the soil. We do have, if we look at it closely, there will be a slight wavy action over there. But it basically it gets bridged by the continuous continuum nature of the soils. It's
Thank you, Dr.
like
Saab. Go
there
ahead,
is a
go ahead.
vertical spring and there is
Go ahead, Dr. Saab. Sorry for interrupting. Go ahead.
Yeah, there is a vertical spring and there is a horizontal spring. I mean, in very simple forms, I can say like this one. So this horizontal spring is holding the vertical spring behavior as well. So that's why it's a reaction, or you can say the profile is almost uniform in case of sigma W.
Your next question is from Miss Kin Sam. She's attending this lecture first time. We welcome him in on our platform. Thank you, ma'am, for attending. And her question is, sir, let me know which type of structure is more effective and accurate by SSA comparison. How can it be validated that it is suitable for structure?
Uh, what type of structure is suitable?
Let me
Uh,
read the question again. Let me know which type of structure is more effective and accurate by SSA comparison. How can it be validated that it is suitable for structure?
okay, let me answer whatever understanding. I think it has two parts. Like for example, what structure she wants to say that what structure is like where we can have a good comparison of empirical versus soil structure interaction. Basically, and how we can validate the results. I think these are the two components of our question.
Yes,
Uh,
exactly.
my answer will be like for example, if we take a simple type of structure, like for example, raft foundation, where the interactions are lesser as compared to other complex structures. Okay, and we can start with it. We can have our constitutive model for the soil. We can have our model for the concrete, and then we do instrumentation and we verify these results. Okay, so this is how we can start validating. We take a simple one, and I always go. That's why I started with the Raft Foundation, because this is the most simplest type of, or simplest in a sense that we can we can work out the validation process using the Raft Foundation. So this is my answer to our question. I hope this would have clarified. Otherwise, I want to say that we can even like for example, we can model other structures also, but there are so many other parameters involved that the validation sometimes become difficult. But again, in general terms, I would like to say that validation is a process. I mean, definitely it cannot for every case. So what is the message is that we should go logically. If we adopt, like for example, a model for the soil, it should be a logical and rational in nature. If we consider structure in our model, the, all the assumptions to model that structure should be logical. So if we are logical in every aspect of the modeling, then we should expect that we'll end up into close to real like results. So you're saying I cannot hear you.
I'm so sorry. I was muted. Just a second. I'll read the question again. Next question is from Rizwan Mirza, and he's asking, soil being known for its heterogeneity, can we realistically predict the actual deformations even when using the relatively complex or sophisticated procedures? The reliability of results cannot hope to exceed the reliability of soil parameters adopted in the analysis. In addition, unless the adjoining structures are included in the model, the potential distress of them cannot be predicted. Is this not correct?
Yeah, I'll start from the end. Definitely, I mean, whenever we are modeling, we have to consider all the different possibility of contributions, whether from the neighboring structures, from the structures underground, or any other, definitely any other contribution. There is no doubt about it. Otherwise, we'll be missing out some of the contributions and we'll be not reaching the right solution. His first question is related with, like, for example, the heterogeneity of soils. Yes, that is a reality. Okay, so that's why, I mean, that's why I mentioned from the beginning, and I think Mr. Rizwan is supporting my idea that soil is a heterogeneous material, soil is an inhomogeneous material, it's an erratic material. So how can we make a very, very simple type of assumptions regarding the soil? We can consider that there are springs, close, uniformly spaced springs, and the soil is represented by this one. Okay, so that's why I also mentioned that the interaction is also very complex, and so we have to train ourselves. We have to teach ourselves that how closely we can predict the behavior of the soil. Okay, the rest trait of the soil, or we can say the rest of the component associated with the inhomogeneity or heterogeneity of the soil, usually we cover through a factor of safety. Okay, and that we determine usually the probability factor. If we have high probability of uncertainties involved in the soil behavior or presence of different type of soils, we increase the factor of safety. Okay, so but there is no compromise on the simplicity or in other words, I will say complexity of the soil models. We have to go with the complex models, and the other behaviors or other traits of the soil we can cover through factor of safety concept. Again, factor of safety should not be constant. It should be based on the level of uncertainty or probability of certain unknown things in our, or unknown behaviors in our cases, and it shouldn't, for example, a fixed number.
Thank you, Dr. Next question is from Tatiana. She's from Belarus and she's a professor herself. She's teaching in some university there, and she's one of our regular participants quite often and on. So first she has said this is an important topic, and then she has asked, correct modeling requires knowledge and experience. I would say sometimes deep knowledge of not only soil mechanics dynamics, but also knowledge of software itself. Who checks the results of modeling performed by an engineer? Is there an independent examination of projects? And she has a second question also that I will ask later. Please go ahead.
Yeah, okay. I mean, she's, I think, again, just sporting the idea which I have uh, floated, that it's a like area which definitely requires uh, input from the experience as well. And I mentioned it somewhere. Okay, so we have to do the modelings, and then we have to groom our models. I will just quote unquote groom our models based on our experience. So as we go on with the projects and have observation from these projects, we'll keep on grooming our models and the constitutive models or the overall models. So there is no compromise on the experience, but just merely based on experience, we cannot move to anywhere. So because before we developed our empirical or semi-empirical methods based on our experience only, and those were never groomed afterwards. So in real modeling, we have to adopt the rational and logical techniques to make it more realistic, and then incorporate our experience or incorporate our experience to tailor or to we can say refine this model for the later use.
Okay, she has a second question also, Tatiana. And no, in the first question, so what is that? Is there an independent examination of projects? What she means that if you have designed a project, modeled a project by an engineer, will anybody else should also check it, or I mean that's a self-examining sort of system.
Actually, it should be like, for example, each project should have a good feedback to the designers. Okay, and there could be instrumentation or there could be journal observations that can tell us that whether whatever we assumed or whatever we adopted in our design, whatever parameters, models, etc., adopted in the design were okay or not. Do we need to tailor these? Uh, Cross verification from others, definitely, if there are experienced people, they can verify based on their experience also. So experience input is required, whether from the projects or from the persons.
Okay, thank you, Doctor, for the clarification. Her second question is, the software market is quite wide. What modeling software is used in Pakistan? What are the principles of choosing software? And what software is most often used in Pakistan?
Okay, uh, that's right. There are many softwares that exist for SSI. Uh, but here, actually, I have listed down the requirements of that software or requirements for the performance of soil structure interaction modeling. Okay, there should be like this software should have a capability of modeling precisely both soil and structure precisely and equally, I'll say. Uh, so this is the first trait that is required for that software. Okay, then it should have uh, enough constitutive models of materials that can represent all different type of soils, or it can cover complete spectrum of soils and rocks, and even the structural elements as well. So these are the requirements. So far, as per my knowledge, I'll not say that this is the ultimate, but as per my knowledge, so far, Plexus 3D is one of the software that can handle most of these traits, or that covers most of these traits, or the traits that are required for SSI modeling. In Pakistan also, people are using Plexus 3D for SSI modeling.
Thank you, Doctor. Next question is from Suhail Kibriya, engineer Suhail Kibriya. He's asking, another point that needs commentary by the speaker is that the relative looseness or denseness of the soil immediately under the mat and contact of the mat with the underlying soil also appears to be an important factor in SSA. Let me repeat it again. Another point that needs commentary by the speaker is the relative looseness or denseness of the soil immediately under the mat, and the contact of the mat with the underlying soil also appears to be an important factor in SSA. What would you say about the safety of existing structures designed under various models of SSA? Dr. Saab.
Okay, sir, the first part relates to the presence of, like, for example, a loose layer. Let me take out this one. File draft is this one. Okay. A loose layer that is present in between raft and basically the other dense soil layers. This is what I understood. So this is again this further emphasizes the importance of such kind of modeling, because it's very difficult. It's very difficult to just consider one spring, or one spring representative of loose layers and very dense layers collectively. So in our real modeling, we can do all this, and we can place, like, for example, a loose layer, and we can see the difference, and then we can have place, like, for example, a well compacted layer, and we can see the difference. So we can model all these scenarios to come up with our rational design. So this is what I understood as regards the part one, or the first part of the question. And the second part, sir, can you repeat the second part? He's saying
What
the
would
last one.
you What would you say about the safety of existing structures designed under various models of SSA?
Uh, okay, so existing structures, again, if I understood again that the existing structures that were designed using empirical methods, right? And
So I think
now,
this is the intent. This is the intent of the question. Yes.
okay, so existing structures that were designed using, so how can we determine that if they are safe, on the safer side, or they were basically over designed at that time? Okay, it's my purely personal experience. I'll just go to this slide, this one, and I mentioned over here that basically, and so many people actually ask not this question. They ask that if we have gone unsafe, we have not seen anything wrong with the structure. But my personal experience shows that usually this basically this problem is basically hidden under the ground. Okay, and usually it is along the column and the foundation interfaces. So if we have to see that our structure was under designed, and then I think better we expose this part of the foundation, whether it's a raft foundation or footings or whatever it is, and we see if there is any structural problem over there. Are there any cracks? If there are any cracks over there, it means that this slope was exceeded. This flow was exceeded, and now these cracks will arrest so many elements that will reduce the durability of the structure. But if there are no, it means that still the structure is intact, and there was no under designed. Definitely it was over designed at that. It could be over designed, I'm not saying, but at least it was not under designed. So this is the way to assess the safety of the structures, or you can say the integrity of the structures, that we have to expose the foundations partly and see if there are any problems over there or not.
Okay. Next is not a question, just a comment. This is from Madam Kin, who is from Thailand. She has said, "Thank you very much for explanation. I got many knowledges from presentation." So, Ms. Kin, thank you very much for your kind words. And I hope that I'm really glad that our endeavor to hold this kind of a lecture has been useful for you. I'm really glad to hear from you. Thank you very much. Next question is from Suhail Kibria. He is asking, will not using different SSA models at various stages of the project result into sometimes cost overruns?
Sorry, sir, there was a connection problem. Can you please repeat? Sorry.
I will repeat it. This question is from engineer Suhail Kibria. He's asking, will not using different SSA models at various stages of the projects result into sometimes cost overruns?
Different models. Actually, if we look at this slide, my last slide, I said that we can have, like, for example, different stages of the project. We can have, like, for example, at the early stages of the design, we can have empirical or semi-empirical approaches just to get an idea where do we stand, whether this project seems to be feasible or not. So this is just for the rough assessment. And I'm proposing that straight away from for any design, we should do the precise designing later on. We should not adopt, like, for example, something in between empirical and the SSI. Otherwise, I agree with him that there could be problems. But I mean, either we have to use our experience, just to get an idea, or we have to do a precise modeling.
Okay, Dr. Saab. Next question is from Rizwan Mirza, and is it a question or a comment? No, sort of a question. The most significant aspect of soil structure interaction under seismic disturbance is the effect of soil period on the response. Does the speaker agree that this is indeed so?
Yeah, of course. That's why you see here in this diagram. In this one, we can see here, of course, response spectrum from response spectrum point of view, or the period of loading definitely plays a great role, because if it coincides with the structure, we can have, like, for example, very large displacements and vice versa. But a problem is this, I agree from this aspect, but the problem is this, that when we go for, like, for example, empirical numbers available for a macro zone, and then use this one for the design of structures, sometimes we may have a mismatch. So that's why the realistic modeling, generally I agree with him, but for specific modeling, we will get the right spectral accelerations against different periods, and then we can compare these with our structures. But in any such modeling like this one, in this slide, we can see in this modeling, we are already shaking our structure in a natural manner. So if there is a problem, from the specific period wave, definitely the structure will show up over there, or it will show up in the form of very high stresses or deflections in the structure.
Thank you, Dr. Habib. Next one is from, again, Madam Kin Sam. She is asking, can I use study for soil cement column?
Yes.
I think, can I study for the, she meant like this. Yes, sir.
if our question is like, for example, can we model a soil cement column in the soil? Yes, we can do. And even if we can do, like, for example, a stabilized soil using cement. We can have a stabilized layer of soil with the cement, or we can have cement stabilized columns as well. So all this can be modeled in an SSI. Everything is possible. But again, the input required is the constitutive or behavior model of that soil, and that we need to determine through some of the testing in the lab. Once we do perform these tests in the lab, we'll get the right parameters. We will update our constitutive model and input that model in the comprehensive SSI model. Otherwise, if we like, for example, try to simulate or uh, uh, try to correlate the behavior of a soil cement with our very famous and very famous model like Mohr Coulomb model, will not get the right results. So every material under different conditions has a different behavior model, and that is one of the most important component which I have mentioned in the last slide, that constitutive model of materials. So that's very important. If we input wrong models, wrong behavior models for different materials, will never end up into a precise model. So soil cement has a lot of different kind of behaviors. It could be like, for example, soft like soft rocks, or it could be very hard like hard rocks. So each of these two materials I mean, it's entirely different kind of constitutive models. So the important model in the variable, otherwise everything is possible.
Thank you, Dr. Saab. Ladies and gentlemen, I'm getting tight with the time. So please, I have received the last two questions and no more questions, please. I won't be able to accommodate within the time span I have remaining. Now, next question is from Rizwan Mirza, and he is asking or saying, if simplification of non-linear behavior of a material was so undesirable, all structure analysis and designs would invite the same criticism. Would you not agree that reasonable approximations are the very basis of all engineering?
Uh, so what my perception is that we make assumptions when we have limitations. We make simplifications when we have limitations, and we had these limitations in the last century. We didn't have computers, we didn't have softwares that can handle all this stuff. So we're trying to simplifying the complex stuff. But since now we have these capabilities, or we don't have the capabilities. We have the software that have the capabilities. We have computers that have the capabilities. So we should make use of these. Complexity is no more a limitation for us now. It's sorry, it's basically in the hand of computers now. Okay, so we just have to think and it will be done. So again, reasonable assumptions or simplifications. Okay, we can do maybe at early stages of a design, and we just to assess uh, some, or make a very general decision. But for an economical and durable type of structure, I think we should be as precise as possible. We are still making, I mean, even in the constitutive models of materials, we are still making simplifications wherever we have limitations of laboratory testing, etc. But again, I'm saying that I mean, the intent of this lecture is we should do as far as possible. We should adopt the complexity of the systems as far as possible, because we don't have to handle. We have an assistant who will be handling, and we will have softwares who will be handling that one. So it's all depends on what exactly we would like to do.
Yeah, it answers the question, Doctor. And now the last question is from Engineer Nadeem. This is the last question. For weak soils with water table not more than 1 meter below ground level, what type of soil improvement technique will be more logical and economical?
Okay, so I don't think so. I mean, this lecture was related with ground improvement techniques. So and uh, but it's not a question that is related with the lecture, I'm telling. But since he has asked this question that for a
Uh,
specific
no, if
what
you, I understand your point. It is not related to the lecture. If you want to answer it, please answer it. Otherwise, we can skip it.
so actually there will be no specific answer to this question. I mean, we cannot say there is a process or there is a procedure. There is a procedure we adopt for the selection of the most economical ground improvement technique for any specific case. Okay, it depends on so many factors. Okay, so it depends on the type of the structure that is there. Okay, it depends on the sensitivity of the structure, or what we say type, nature, and sensitivity of the structure. Okay, the budget available. Okay, the time available for construction, the contractors available, the material available for the improvement. Because if I say, okay, you have to do stone columns, you may not find a stone columns contractor in the area. If I say it's dynamic compaction, I'm just throwing a general idea. So it depends on so many. It's a big process, and we move from, like for example, we start with the shallow foundations, and then we
Thank
move to
you.
the feasibility raft foundation, then we move to ground improvement, and then among ground improvement we can have different cases. So there are many steps to be adopted before we reach a conclusion that there is ground improvement required, and then what type of ground improvement techniques are possible in a specific for a specific site, and then we have to go one by one and do the economic analysis for that one. So it's a very general answer I have given you. So there is not a single size that fits everywhere. So we have to choose a technique after going through this all complete process.
Thank you very much, Dr. The lecture was very enlightening and very knowledgeable. And the interactive session was also, I think, was done in detail. And I really hope that this lecture would have given new insights to our audience and to the geotechnical engineers. Now, before I make our closing announcements, I would like to encourage everyone who has not yet become an associate of our society to consider joining. It's simple to become an associate, and a procedure is outlined on our website, which is psce.org.pk. The annual fee is minimal, covering only administrative costs. By joining PSCE, you will also have the opportunity to contribute to the civil engineering profession through our various committees, where you can actively serve and support our shared goals. And don't forget, we have a WhatsApp channel where which has, I think, more than 300 members now, or around 300, and where very high level technical discussions, question answers sessions take place. So I would again encourage everyone to become a member of our society, associate of our society. Now, information about the next lecture, it is on 14th December 2024. The topic is From Engineering School to Practice, Training Needs of a Civil Engineer in Shifting Paradigms. I repeat, from engineering school to practice, training needs of a civil engineer in shifting paradigms. And our guest speaker would be Dr. Naveed Anwar, 14th December 2024. The certificates for today's lecture can be collected from 21st November 2024, which is Thursday, from our Office 14A1, Block P, Model Town Extension, Lahore. And before coming, if somebody wants to call to find out whether his certificate is ready, he can call Ahmad Akram on his cell number 0347-462-5111, which is 111. 0347-462-5111. So, Dr. Saab, your shield, inshallah, will be sent to you by special messenger, and your certificate also. And I would again thank you for giving such a enlightening lecture with full of insight, knowledge, and and from the questions, I can understand that people have appreciated, our audience have also appreciated your lecture. Now, now it brings today's program to a close. And before we end, I want to give special thanks to my team, which is working behind the scenes for making this broadcast run so smoothly. Inshallah, we will see you again on 21st November 2024. Dr. Habib and audience, Khuda Hafiz. Allah Hafiz.